Here we go. 6.3, we're going to talk about binomial and geometric variables. So there's a lot of formulas and stuff like that you'll see. Cool thing about it is you have to know how the formula works. We don't really have to use the formula in order to calculate the probabilities because your calculator does this stuff. It's pretty awesome. Alright, so this is what we're going to do in this section. Some stuff, and then some stuff, and some more stuff. Alright, so before you can use a binomial distribution, you have to make sure that you are working in a binomial setting. In order to do that, what you got to do is check your bins, okay? So, you got to check to see, is it binary? In other words, is each outcome labeled as success or failure, right? So, the probability that I pull an ace out of a deck of cards falls under that category, right? It's either an ace or it isn't. There's no gray area. Are the two, is the probability independent of other things, right? So if my variable is, if I'm looking to pull an ace out of a deck of cards, right? And I want to know the probability of pulling an ace out consecutively. If I don't replace that card, then the two events are not independent, right? Because the probability of pulling an ace the second time changes. But if I put the ace back in, then it is independent, right? So check for that if each trial is independent. All right, and then N stands for number. Is there a set number of trials, right? Am I going to pull an ace out and put it back in the deck 10 times and see what the probability is that I get 4 aces, the probability that I get 3 aces, things like that. So that's the type of scenario that we would be dealing with, right? Where each trial we're looking for an ace, and we're going to say, hey, we're going to pull it out 10 times, pull the ace out 10 times. What's the probability that I get 4 aces? 3 aces, right? And that brings us to S. Is there the same probability of success in each trial? And the answer would be yes for this one. And that's it on the AP exam. If you use a binomial calculation and you do not check bins, you will get deducted points. We're going to start to get into situations where before we can perform calculations, we have to check conditions. If we don't check conditions, then we've done something else. So I think this is the first point where we've really come to where now, if we don't check a condition, we get points marked off. And you're going to see that now for the rest of the course. Most of the things that we'll do, if you don't check conditions, you will lose points. These are from the season. Where do you go? Okay. So our binomial random variable we will represent as x, and x is going to be the count of successes during our set number of trials. Yes, that's a really thing. And yeah, we do have parameters n and p, n being the number of trials, and p being the probability of success for any trial. That's why it is important that that probability be the same. Not too far. Alright, so in this particular example, you're shown how to calculate a probability in a binomial setting if you were to just calculate it like old school style. But now, we have some new tools that will help us out. So we're going to come back to that. We'll look at another example like it. If you would like to go back, like if you're in watching the video, if you'd like to go back and then use your calculator to calculate this, that's fine. I'm confident because of Chapter 5 you can calculate this probability the standard way. I'm going to show you a faster way to do it. And we're going to use the formula for a binomial probability. So you honestly don't really need to know what the binomial coefficient is. The next formula I'm going to put up, you really need. This one, not so much. Because your calculator is going to do this for you, okay? I'll explain to you what this is. It's, this coefficient is the number of ways, right, that you can arrange k things among n total, right? So you have n total things, right? And you want to arrange some k pieces of them. It'll tell you. It's referred to as a combination. There is actually a button in your calculator that will calculate the binomial coefficient. But really, for our purposes, we don't need to get too wrapped up. Anything cool? No, you can say that. This you need to know. And you just need to know what the pieces are. You need to know how to substitute values into it. This is on your AP Statistics formula sheet. Yep. So you don't have to memorize it. Good news. I don't have it memorized because I know that I'm allowed to look at it on a formula sheet because you're allowed to look at it on a formula sheet. So that's kind of the way I roll. For example, the way that I would use this, well, I guess that'll be an example on the next page or something like that. So here's your formula. All right. How do you find your binomial probabilities? And this is the crazy thing right here, okay? So you can input that stuff into that formula, or you can do that. That is going to be the easiest way to go. It just, honestly, in order to answer the question, if it tells you, hey, LeBron James is shooting free throws, he has a 74% chance of making a shot, what's the probability that he makes 8 out of his 10 shots? Let's see, perfect example of a binomial probability problem. All you got to do is put all the necessary things in the calculator and then actually write what you're putting in your calculator. That is a perfectly acceptable response. So if we were to go through an example, this is what it's going to look like. I'm going to do an example of a problem. So here we go. We've got a particular pair of parents that have a probability of 0.25 of having blood type O. Suppose the parents have 5 children. Find the probability that exactly 3 of the children have type O blood. All right, so first of all, and I don't know why they're not doing it in these, but you really should check that binomial setting is appropriate. Is this situation binary? Yes. It's either they have type O, the child is born with type O blood, or they're not, right? Second, is each trial independent? Yes, because having a child that has type O blood does not affect the probability of the next trial. Is there a set number of trials? Yes. They're only having 5 children, right? They're not going to have infinite children. And then S is the probability, so success. Is the probability of success the same for each trial? Yes. Each time they have a baby, there is a 1 in 4 chance or a 0.25 chance of them having a baby that has type O blood. So there we have checked it. This particular problem is going to go ahead and use the actual binomial formula. I am right now going to go ahead and demonstrate to you how to do this using your handy dandy Texas Instrument calculator. Well, I was playing this. What do you what? Yeah, no, I left you out on purpose. Alright, so in order to do this, we can do this just using our scratchpad. You don't need to make a new document, anything like that. Just using your scratchpad, we're going to do this. And what we need to do is determine what n, it's determined on this, what n and p are. Oh, that is jumping ahead. Okay, sorry. In this case, n is 5, p is 0.25, and x is 3. Okay? So we can do all of this on our handy-dandy calculator. And saving us loads of time and effort by hitting menu. We go to probability, and then we go to distributions. If you scroll down, you will have binomial PDF. You will hit enter. Number of trials, n, in this case, was 5, right? They're going to have 5 babies. Probability of success is 0.25. And we want to know the probability that they have 3 babies that have type O blood. We hit OK. And there it is. Okay.
So what's the difference between PDF and CDF?
Oh, we're going to do a CDF one here in a second. Good question. Guys, all you need to do on the AP exam or any exam to get full credit on this question is write that. That's it.
That's it?
That's all you have to do.
And you can just do that.
Yeah, you do not have to do all of that. So this example is using the formula. You do have to understand how to, like, what goes in that formula, but that formula is right there. Probability x equals 30, n is 5, k is 3, p is 0.25. So you could input those values in there, write in equals, and then use your calculator to calculate it too. If you wanted to actually, like, if you felt like you didn't completely do it without filling some stuff into a formula, right, you could do that, and then just write your calculator in. But just this is a completely acceptable response. Yeah.
So on the exam, do they give us calculators?
I will give you these calculators. Yeah. Yeah, I will assure that you have a TI Inspire calculator on the test. I will bring them down for you, or if it depends on my schedule and what time the test is. The test is usually in the middle of the day. I think I'll be able to personally bring them down there for you.
Okay, and we're allowed to use Inspires on that?
Yes, Inspires are fine. You cannot use and Inspire cats, but I don't have any of those. So the CX is what you have, and that's what you'll be able to use. You'll use these very calculators. All right?
I think this very long.
Yes.
Do we have to clear it out before we take the test?
No, I'll clear them out for you.
Darn it, Mr. Clinton.
And the day before the.
You got a program on.
Yeah, I know. So we can see that our value matches their value right here. And now, you ask, why would I use binomial CDF? You saw that there. Well, if we want to know that more
Oh, wait, you're going to ask
than 3 of the children, right? So, that would mean 4 or 5, right? So you could calculate the probability that x equals 4, and then add that to the probability that x equals 5, or you could do that all at once using your calculator. And here we go. We'll go ahead and do it. We'll hit menus. We'll hit probability, distributions, and then we will go
Oh my god, oh my brain. Josh, you have to watch that one that I just did.
Binomial CDF.
You're gonna freak out.
Again, my number of trials is 5. My probability of success is 0.25. My lower bound now is going to be 4. My upper bound will be 5. We're talking from 4 to 5, right? More than 3 is going to be from 4. I hit OK. And I get approximately 0.016. Again, this is an acceptable answer. That is an acceptable answer. College Board will take that answer. It's pretty good. And that's the answer they got with a lot more work. So, efficiency. This is what this distribution, what a distribution looks like. What is this one? This is for type O blood. So this distribution looks like this. Always interesting that when you look at a binomial distribution, the probability of 1 is normally greater than the probability of 0 of the events occurring. Kind of interesting. And it turns out that as you add events, right, as this distribution gets larger and larger and larger, it turns out that you can use a normal distribution to approximate these as well. And vice versa. And I think we say that here in the next thing. We'll look at mean and standard deviation here in a little bit. This is the long way of doing it. There is a shorter formula, and here it is. Again, these formulas are on your AP formula. You do not need to memorize them. I will show you exactly where they are.
With Mom always leave me out of it, like I know you know my name, just like don't send it to me. And then
Right.
she kept doing it and doing it, and I was like, oh Laura, I know you stop.
So there's an example of calculating mean and standard deviation. We'll do examples when we go through the example portion. It's really not hard. This is going to come up later, so you don't have to worry about it too much now. This 10% condition is,
Do you want it or not?
honestly, you're not going to do this. Alright? If you have a normal distribution, if you have a normal distribution, you're going to use normal probability. You're not going to use, it would be, I don't know why, you would use a binomial distribution. You would approximate it as a binomial distribution. Yeah, if you can assume that the population is normal, then you can also use a binomial distribution. But you're not really going to want to do that. This is y. Here's a picture of it. Right, as n gets larger, you can see that the distribution looks more and more normal. And that's just y. Again, this rule of thumb, this normal approximation rule, we're going to get into so very much when we get into inference. So we don't really need to touch on it right now.
Are you gonna be running?
Here you go, it's the geometric setting. The only difference between your geometric setting and or the main difference, I should say, between your geometric setting and your binomial setting is that instead of saying, hey, what's the probability of getting 3 successes? So for instance, with the LeBron James thing, then what's the probability, you're being asked, what's the probability that he makes it on the second time, right? What's the probability that he makes it? So he takes 10 shots. What's the probability that he makes his first shot on the 8th try? You can imagine that probability is going to be really, really low. That's the same as the probability that he misses 7 shots, right? As we go through our examples for each of our binomial settings, I'll go ahead and throw in a geometric probability as well. So yeah, we're looking at the number of trials that it takes to get your first success. That's all the geometric. I feel like we're good. This is what the formula looks like. You really, really don't need to know. There's no reason for you to know. I'll show you how to do it using your calculator. This is what a geometric probability looks like. The distribution, I should say. You also don't need to know mean. You do not need to know the expected value of it. None of that. Okay. All of this is extra stuff. So don't worry. Now we finished.
I told you we finished.
Did you notice there wasn't even an example of how to calculate probability using geometric distribution? I'm going to give you plenty of those as we go through binomial distribution problems. I'll throw in an extra one in there where we say, what's the probability that a success happens on the kth try? So we'll do it like that.